So we are here today to talk about visualization in AI. And as I said, anytime I'm starting in AI projects, anytime I'm like, okay, I got to build a prototype, the thing I have in my head is like, which visual do I need to work up to? Because a lot of AI is about using visuals to figure out, okay, what is going wrong? So AI is like a very iterative thing. First time you're just hashing down it's like a model and it's just, okay, just get the data in and get the input out. Okay, that's all we need. Just move the data and don't throw errors. But then later on, we also gotta make things work properly. So the next lesson, we're actually gonna talk about exactly, what we need to make work properly. But today, I wanted to make sure that we have the same frameworks, that we have the same basis for understanding the visuals. Because there are some visuals in AI that, we've never seen before, like literally. And this is like the part where math and philosophy intersect. So you'll have to pardon me as I go on some tangents, occasionally. I'll try to limit it. But let's get started sharing my screen and we'll start and take it off slow. All right. So this lesson, I called it visualizing scalars and vectors. And the first thing that we got to do is remember what a scalar is from last lesson. Scalar just means a number that is not a group. Okay, it is one single data point. So for example, we have this variable a and we set it equal to 2. That's just one number. And the thing that you got to keep in mind about a scalar is it's one dimensional. So you can literally represent it on, a number line. Here's 1 point. That is it. That's how we visualize scalars. Not too hard, right? We're doing fine, right? Maurice, you're not confused. You got it. One dimensional, one line. Makes sense. Sounds good. So, we're used to this. We're used to this. But what happens if we then go and we want to be weird, okay? We want to go from a scalar to a vector like this. Now there's not just one number, there's like this one number in light green and a number in dark green. What are we gonna do? Now, here's a quick note. I just have this like random arrow here over the vector. That's something that you see often in physics. It's not necessary in computer science, just so you know. If you're ever seeing vectors in math or physics, you might see it with this arrow on top. Just means a vector. So when you have these two numbers, keep in mind what we did here. Like we were making a point. And now, if I think about points, what I'm thinking about is like all those grids that we draw. Like, you know those grids, right? Like we do 1, 2, and we put a point here. Cartesian planes, you know those? Well, oftentimes we also have two numbers in those grids. So what if instead of having like this weird vector thingy, one row, two columns, what if we set it in parentheses notation, just like we do with all those like coordinates that we're always working with? So here's something you should know. Here's just a cool thing. This and this, so this notation and this notation, they actually mean the same thing. You can actually define vectors with this symbol or this symbol. And I know that just sounds weird and arbitrary, but for me, like programmer head, that makes a lot of sense. And maybe if you're programmers, you might think that way too. I'll show you soon what I mean when we get to the Python lesson. But basically, all of this is just saying the same thing. When you have a vector and it's 2D, 2D because there's 1 point in light green, 1 point in dark green, instead of just 1 point, then you can also exchange that for those coordinate notation that we always see with Cartesian planes. And if we do that, well, we can make a graph. Yay! You see, we got a graph. So here we don't have an x and a y axis. Instead, what we do is we break down these vectors into what are called components of a vector. You can also say elements, like that would be a more mathematical way, but a more physics way might be saying components of a vector. So let's say like we call this component Vx, V subscript x, and we call this component Vy, V subscript y. There we go, we got two components. So now we can go, okay, this means go 1 this way and go 2 up, and there's our point. Make sense? So here's something that you should keep in mind. When we're drawing these points, what we're really saying is just what I said, go one this way, eh, and then go two up. Eh. So when we draw this, it's like vectors. They're like a sequence of arrows, okay? In physics, we call it like, you add together these arrows, these components of a vector, and it's like you start at the tail end here, go to the head of this arrow, then you add the tail of this arrow, and like you go to the head here. And overall, you get this total vector like this. So what I'm essentially saying is you can view vectors as coordinates on a grid, except those coordinates aren't just points, okay? You can make those coordinates into components of a vector like Vx, Vy, and they just mean, okay, you go this much in the Vx direction, you go this much in the Vy direction, and if you combine those, then you get the overall vector, which we can represent as an arrow. Is this making sense? All right, Therese, you don't look so convinced. Everything cool? Yeah? So here's like a philosophy bit. Here's the first philosophy bit. This vector notation, it means the same thing as this like parentheses, coordinates notation, which means the same thing as this one point, which means the same thing as all of these arrows. They're all representing the same information. Why do we have so many different ways of representing one information? Why is it so much easier to understand this than just like this, oh, there's like a square bracket and a 1 and a 2. Philosophy points. Philosophy. Philosophy points. Think about that. Now, let's say we extend that, okay? So over here, what we did was we had a 2D point, 1, 2, we have 2 data points. Let's say we have a vector in 3 dimensions. Eh. So, 1 dimension, 2 dimension, 3 dimensions. Again, just have a random arrow. You don't need it. Now, just like I did here, where I moved that vector as a coordinate, I displayed it as a coordinate, I can display this vector as a coordinate too. And now here's what you should be thinking in your head right now. So wait, what he did before was he took vector, turned it into coordinates, put it on a graph, and then broke the graph into arrows. So guess what we're gonna do? Vector, coordinates, we gotta get a graph with arrows, except it's gotta be a 3D graph. So let's see. You see when I have my browser up, right?
No, we still see paint.
Okay, let me stop the screen share and make sure we have the browser here. Share screen, like this. How about now? Yeah,
Looks good. Now we can see both.
that's good. So I gotta get this URL. GeoGebra.org/ready. Aries, do you mind memorizing this back half? So I'm gonna get SY6, you get the rest. We're gonna collaborate, okay? This is teamwork right here. SY6. Aries, what's the back half?
GHFXF.
All right. Hopefully this works. Please, please, please. I think it's working very slowly. All right, we're here. So this is GeoGebra. It's just like a place where we can make graphs and stuff. Nothing too fancy. It's also very slow, which is fine. We don't need internet speed. We don't need things to be fast. Am I right, guys? We need speed. All right, we're here. So look what we did. Exactly what I said. Now we have a point, just like, we did before. We took the vector, visualized it as one point. And the reason is because the vector, we can describe it as like a 3D point, this is a coordinate, yeah? Coordinate goes on graph, turns into points, visualization. And as ever, We can also describe this coordinates as a bunch of arrows. So we can describe it as an arrow along, let's say this is the x-axis. So you see that red arrow just appeared. And then we can add another arrow on top of it that is on the y-axis in green. And then we can also add another arrow on the z-axis. Yeah, z-axis. So you see, now we have 3 arrows being used to describe this one vector. And we can also add together those 3 arrows into one combined arrow. You can see it goes diagonally because it has 3 components, one this way, one that way, one up, and it's diagonal. You see, all of these represent the same information. A point, this one vector, the components of this one vector, this coordinate system, and the vector notation itself. Sound good? All right, now we're gonna really mess with things, okay? So this is like just basic level stuff. Now what do we do if we have functions? You remember functions? Well, those things that I was like, oh, y is equal to x squared, but this one's like f of x is equal to x squared. So let's say we have our old friend, f of x equals x squared. We should give him a name, or her a name, or whatever mathematical notations are called. We should give them a name, because it comes up all the time. Anyways, f of x is equal to x squared. Notice what's going on here. X, the input, is a one-dimensional scalar, so f of 2, and then the output that we get from the function is also one-dimensional, x squared. So if we put in the scalar 2 here, we get out 4. So we can do what we did up here. One-dimensional, you must be thinking number line. Yeah, that's how we're going to visualize it. So if we move x from 1 to 2, then f of x moves from 1 to 4, because 1 squared, that's 1, 2 squared, that's 4. And now, if you think about it, this looks a bit odd. So you can see like a little bit of a relation. It's like I do a tiny nudge in x, and then f of x, the output, it changes a lot more. But this is a pretty inconvenient way to represent one-dimensional information versus one-dimensional. So guess what we're gonna do? You know it. We're gonna combine, the axes. So we just had a number line and a number line. Now we've got a combined number line. F of x on this axis, x on this axis. And here is our lovely shape. So, you plug in 0 into the equation, 0 squared equals 0, 1 and negative 1 squared equal 1, and 2 and negative 2 squared equal 4. And, we can extrapolate a smooth curve. Think about it again. This is just arbitrary. Some person just decided one day, hey, why are we having like these number lines move independently? What if we tried like putting one number line and like another number line? And we could switch them. We could be like x and then f of x here. There's no reason for us to visualize information in one way or the other. This is saying the same thing as this is saying the same thing as this. Isn't it amazing? Isn't that cool? Isn't that like unequal? Like some person back in the 1500s is just like, you're gonna learn this your entire life and no one's gonna tell you why. Isn't that unfair? Like, you don't need to treat it like that. You view it as like 1D in, 1D out. Okay? Let's have like freedom of choice here. We can do all of these things. We got to choose which one's most useful. And now let's switch it up again. So before we had one-dimensional in, one-dimensional out. How about we go to our old friend f f of x and y is equal to x squared plus y squared. Now listen, two-dimensional input, you have one number here, one-dimensional output. So like you put in 1, 1. So those are two numbers that go in. However, you just return 1 squared plus 1 squared is equal to 2. That's just one number out. How are you going to visualize this? This is weird, isn't it? Yeah, thank you for agreeing with me. It is weird. Any ideas? Avnish, go for it.
Um, so we could have a 3D graph with, I mean, I feel like I'm defaulting to the most obvious, like the one that we've been indoctrinated into, but like a 3D graph with X and Y as the inputs, and then the Z axis, how high would be like the output.
Yeah, yeah. That's actually not the default. That's the second order extrapolation. So remember, x comma y, that's the same thing as like a vector going in, right? So what we could do is that we could take the scalar output, the output here, it's a scalar, you return one number, and that could be a number line. And then, the inputs, as Avnish said, we can graph, okay, x and y. So this is one pair, x is equal to 1, y is equal to 1, but it could equally be x is equal to 4, y is equal to 3. So you have like different possible combinations on this set of axes. However, I like Avnish's combination better because like this combination is like, like I can move this around here, but I don't really know what's going on over here. Like it seems a little bit disconnected. So let's do exactly that. Uh, let's memorize this again. HF7, I got that part. And Aries, you gotta get the other part for me. HF7, I got that part. HF7. Oh, wait, Aries, you can't see the other part.
WX5KE, but yes, yeah.
WX5KE. So we're gonna, again, give GeoGebra time to load, but it's exactly what Avnish was saying. So we just arbitrarily decide, for some reason, that we're gonna have like those two set of axes in one location, and then we're gonna have the other number line going vertically. So here you can see the red line and the green line. So that's X, that's Y. And what I've done here is, let's say I choose like a particular set of inputs here. So A and C are particular values. So you can see A is the point 1, 1. So X is equal to 1, Y is equal to 1. And over here, C is equal to 1, negative 1. So X is equal to 1, Y is equal to negative 1. Now, A and C, what they represent are the inputs. I can color code them for you. So let's say everything in green is the inputs. Like this. And let's close this up. So let's say everything in green is the inputs. And then B and D are the outputs. So remember, what we're doing is square the X, square the Y, and then we get out just a scalar number. So we want X squared plus Y squared. And guess what we get out? X squared plus Y squared. So if we have like 1, 1 as the input, 1 squared plus 1 squared is equal to 2. That's why D has a Y value of 2, because that's the output. And then same thing on the other side. If we have 1, negative 1, so X is equal to 1, Y is equal to negative 1, the Z value is going to be equal to, in blue, the Z value is going to be equal to 1 squared plus negative 1 squared, which is still 2. So you can see here, I have the inputs, in green and these outputs. And the output is represented by the heights above the plane. Make sense? So now here's like a fancy trick I'm gonna do, okay? This is like Jedi trick. What I'm gonna do is instead of like just taking one coordinate, one input, say x is equal to 1, y is equal to negative 1, what if we did what we usually do with graphs, which is we do it for all coordinates. So, not only one value of the input, but all values of the input. So all pairs of x and y. Here's what we get. Ah, that's cool. Let me zoom out for a bit so you can see. Yeah, is that zooming in? That's zooming in. You see what the surface is? The surface just means, okay, I'm gonna take any value of X and Y, and then I'm gonna put a point on this like orange graph above for the Z value that I get out. And you can see it looks a little bit like a parabola. And that's not by chance because we're always doing x squared plus y squared. So you can see kind of why it looks parabolic. Isn't that cool? It's like a 3D surface that we're creating with a function. Did you know you could do that? Did you know? Like you know all those CAD softwares? I've been messing about with CAD recently. How do you think they get those surfaces? They gotta use 3D equations. So that's a cool application already. We can make surfaces when we have a two-dimensional input and a one-dimensional output. Now let's start messing even more, okay? So two-dimensional input, one-dimensional output. That was before. By the way, we're gonna come across lots of graphs like this later on. And that is fine. But what if you wanna, you wanna go full 2D, okay? Two-dimensional inputs and two-dimensional output. So let's make sure we're understanding what's going on here. This function is basically a doubler function. So you pass me some value of a and b, I will return like double that. So 2 times a and 2 times b. So I have a 2D vector going in, 2D vector coming out. Yeah, a function can do that. It can take a vector in and it can return a vector out. So for example, if I put in 2 and 3, then 2 gets doubled to 4, 3 gets doubled to 6. If I put in -3, -1, -3 gets doubled to -6, -1 gets doubled to -2. Any ideas? What are we gonna do with this function? 2D in, 2D out. We haven't ever seen more than 3 dimensions. That's not how the world works. What are we gonna do here? Any ideas? By the way, there's multiple answers. Avnish?
This is tricky. I'm thinking. So we know how to visualize 2D vectors.
Yeah.
Right,
And let me show us again, how do we visualize 2D vectors? As points or as arrows? Go on.
right. So what we can. So we can put an input vector there, and then we can have another plane for our output. But
But they
then
won't be connected.
Yeah, it wouldn't feel connected at least.
Yeah, so it would be like, okay, I have one input plane, and I would put like 2 this way, 3 that way. I put a point there, and then we have a separate output plane, and like maybe 4 this way, 6 that way here. That's one possibility. Any other ideas?
Maybe connect them somehow. I'm not sure how exactly that would work, but
Loop to loop.
Thanks.
Connected. Sorry, that wasn't to criticize your idea. That was just me drawing because I like drawing. Yeah, so we got to connect these somewhere. Now it's a little bit hard to like connect 2 points. So there are 2 things that I'm thinking of, okay? Here's one thing. Here's like some sensible thing often people do. You could have a 3D graph, and then instead of adding a 4th dimension, maybe you could represent like a 4th point randomly. So like this is X, this is Y, this is Z, and then this is like the color of the dots you put on. Or maybe it's like the size of the dots. But it's a little bit weird to do that because like, you're taking 2 of the inputs and making them axes, and then 1 of the output and making it an axis, and like the last one is just like, yeah, whatever, I'll just be a color or something. So here's another approach we're gonna try. This is a really key idea in physics. If you're ever gonna go into engineering, you're gonna learn about this. So remember, vector, this is equal to this, is equal to the points, is equal to the arrows. So what if we like represented the input vector and the output vector in different equal representations. So maybe 1, the input was a dot, and 2, the output was an arrow. Let me show you what I mean. So let's say, after we scroll down a lot, we have the inputs 2, 3, okay? We're gonna make that a point, and we're gonna make this a vector. Here's how we're gonna do it. So first, I know it's hard to see, but that says that's the b-axis, the second input parameter, and that's the a-axis, the first input parameter. Parameter just means a variable that we can change. And what I've done here is made this 2 and then 3. So I'm representing the inputs in blue with these blue points, okay? So that's the first part. That's the first part of the problem solved. We're representing the inputs as dots. Now for the outputs, here's what we're gonna do. We're still gonna use another equivalent way to represent vectors, but we're gonna do it in green here. We're gonna make arrows. So the blue thing is the input. And on top of that, we lay a vector. The vector is the output. So let's focus on 2, 3 for a second. So again, we double. So if I have a coordinate at 2 and 3, 2, 3, then I gotta make a vector that has an x component of 4, because that's double of 2, and a y component of 6, because that's double of 3. So that's why I go 4 to the right and 6 up, and that's my output vector. This in green, 4, 6. 4, 6 is equal to this. You see? That vector is equal to this arrow. And that vector in blue is equal to this point. Same thing over here, okay? So again, -3, -1, I graph the point, and then the arrow, I needed to have an x component of -6, a y component of -2. So what I did here is I went 6 to the left, -6, and then down to -2, and I made another vector arrow. Now, keep in mind what we did before. You know, we didn't just want to have, sorry, Avnish, do you have a question?
Yeah, but I felt like maybe you were about to answer it. I think the thing that I find interesting is the tip of the vector is not pointing at like the point that it represents, right? Like for example, this vector
Mhm.
for, I believe it was 4, 6, right? But it's not the point, the tip of it is not at the point 4, 6. It's just like the
Yeah,
components are 4, 6, right?
yes, that is correct.
Okay.
So remember with vectors, they're representing more so like a direction. So I could have like this vector actually start over here, right? Do I have a color here? That's a color that I don't understand. That's a good question. You know, why isn't it starting and stopping in a predictable way? But I could honestly have like a vector start from this point. It also goes over by 4, 1, 2, 3, 4, and it also goes up by 6. And you could get the same like angle of the vector and same size, you know, same length, but it's just starting and ending at a different place. So vectors don't actually need to start and end at any one place. Cool tidbit. So that's one thing. And that's a good observation. However, there's another issue. So that's one issue. The vector output doesn't correlate with, you know, what actually is the point that is being graphed. The other issue is, remember what we did before. We didn't just want to graph like 2 points and their surfaces. We wanted to graph a point and then all of like the outputs. And you know, look at what we already have. Like these output vectors are taking up the entire grid. Imagine if we had like a point here and one here and like one here. Like it's gonna get really messy really quickly. So what we do is we still want to keep like the direction of the vector that we use as the output, but you know, we don't want to have like all these vectors crisscrossing everywhere. So what we'll do is like we'll use color to code for the vectors. So if you have a longer vector, it'll be like a warmer color. If you have a shorter vector, it'll be a smaller color. And here's what it looks like. Oh, cool. So what we're doing here again, so each point, that's the base of that's the input point, that's the input point, that's the input point, that's the input point. We have lots of input points. We double the input and get an output, and the output is represented by a vector. But you can see these outputs over here, if you have a larger X value in, you can see it down here. Well, it's very tiny. You can see down here, X is equal, A in this case is equal to 4. So when that is bigger, then you're going to get a bigger output than when you have A is equal to 1, which is why as you get further away from the as you get further away from the origin, the vectors get longer, and that's why they're in red. And in case you're wondering, like it's the same direction of the vectors. So you see here, this point I've marked, it's 2, 3. I'd show you each of the axes, but the numbers are small, so trust me, it's 2, 3. And look, it's going like in a 45-degree-ish direction. Up here, 2, 3, 45-degree-ish direction. Yeah, same vector, just we've color-coded the output. And down here, -3, -1, it's like in a 30-degree direction, down from the horizontal. Same thing here. This is about a 30-degree-ish direction, down from the horizontal. So it's the same direction, but the magnitude is color-coded. Magnitude is what we call the length of the vector. Cool? This is called a vector field. Any questions?
Yeah, so I guess is there like a problem like with these that, for example, like the vectors on the far right,
Mm-hmm.
it's not obvious, okay, that point, like exactly where is it going? Because color is not like as precise as what we're used to, I guess.
You're not sure where this point is going?
Like I know it's going that way, and I know it's going like, because it's red, it's like big, right? It's going farther than, let's say, a point close to the origin. But you can't really tell exactly how far, can you?
Yeah, so you can't tell like where does the vector end up? And that's the downside of vector fields. Now, this is going to be the last visualization today, so I want to give you an actual like example of where this is used. An example of where you might use a vector field is, let's say you're measuring magnetic field strengths. Okay, I don't know if you've ever seen magnet filings. I want to show you magnet filings. Okay, magnets filing pattern. You know those rings that they form out? Have you ever seen those rings? You see lines of force over here? You see these rings? That's almost like points on a vector field. If you can imagine, it's almost like over here, like you have a point and like you have a vector in this direction. Over here, you have a point and the vector is like more, it's more horizontal. Over here, vector has a angle like this. This is kind of what we use vector fields for in physics. So we can represent magnetic field strength with an equation, and like we'll get out a bunch of vector points, and they will point in the right directions to show the magnetic field lines. And the colors will show the intensity, but because this is a force, we don't need to know, okay, like, the vector starts here and it ends there, because it's not representing like, motion from one point to another point. It's saying at this point, here is the strength of the electric force or the magnetic force. And, it goes in this direction. That's like a cool practical application. So that is the end of our lesson on visualizing different types of inputs and outputs. Now, what I'm going to do, and the entire reason I showed you all this, is because we need this to be able to understand how gradient descent works in machine learning. So what I'm going to do with these lovely people here is I'm going to show them a video, off screen, and maybe I'll record it, maybe, but I'll definitely post this in the link if you want to check it out. It's a Khan Academy video that perfectly explains how gradient descent works and what actually is a gradient of a vector. All right. All right, so I'm going to stop this recording here, and maybe we'll record the next one. So that's one there. I'm gonna, oh, I didn't stop the recording, I just stopped.